Hello students, my name is Alpa Rupala, Assistant Professor from LG Institute of Engineering and Technology, Computer Department. Welcome to the lecture series of Mobile Computing and Wireless Communication. Unit number 2, Subtopic Cellular Wireless Network. Topics to be covered in this lecture. First of all, the line of sight significant impairments and then after fading. So in previous lecture, we have learned about the propagation mode. We are having three types of propagation mode: ground waves, sky waves and line of sight. As we have learned earlier that these particular propagation modes are very much dependent on the frequency. Like if I tell that my radio signal frequency is less than 2 megahertz, then my waves are according to ground waves. Then my waves are moving along with the ground. So it is ground waves. If my frequency range is from 2 to 30 megahertz, then it is sky wave propagation, and if my frequency is greater than 30 megahertz, then it is the line of sight. So we are talking about line of sight propagation now. That what the line of sight propagation are having impact as the attenuation by the significant impairments. There are basically two type of impairments can be there: when obstacle are present and when obstacle is not present. So first of all, we are seeing about the when obstacles are present. So the blocking or shading effect can be there, reflection can be there, refraction can be there, scattering can be there, diffraction can be there, multiple path propagation can be there, and noise can be there. And when there is no obstacle is present, then attenuation and attenuation distortion, atmospheric attenuation and free space loss can be happen. So first of all, we are learning about the obstacle present impairments. So first impairment is blocking or shadowing. We are having blocking of your signal or shadowing of your signal when the signal is striked on your obstacle which is of very large size. Okay, of very large size, but even for a higher frequency, a small object can also block your signal. Okay. Next fundamental is reflection. The reflection is there when the wavelength of your signal is smaller as compared to your object. Whenever your signal which is having the lesser wavelength than your obstacle, then the signal is being reflected and the signal is being weaker. Next one is refraction. When a signal is moving from lower density medium to higher density medium, then the signal is bent towards the higher density medium. So this particular phenomena is known as refraction. Now next one is scattering. Scattering is being assumed when your wavelength of your signal is very larger than the obstacle size. Likewise, in this example, your signal is being struck on your smaller object and it is being scattered into a multiple weaker signal. Same particular fundamental is known as diffraction, but the diffraction is being measured at the edge of your big obstacle. Likewise, this is a big mountain. On this edge of this mountain, your signal is being struck out and it is being propagated into multiple direction by scattering. So the scattering and diffraction is a similar fundamental, but the diffraction is being happened when your signal is being striked on the edge of your obstacle. Next important impairment is multipath propagation. We have just seen about the reflection, diffraction, scattering, all the fundamentals. So it is like that when you are traveling from one place to another place while you are on going call and you are getting the signal from a tower nearby your area. So this particular tower is sending signal to your place, but this tower signal can have multiple obstacles to reaches to you. Suppose in your example, you are having multiple signals. A single signal can take any of the path because we are in a moving condition. So your signal from transmitter to receiver, suppose you are having the signal A which is reaches to your receiver in a directly straight path. Okay, suppose you are having a signal B which is being reflected by one obstacle and reaches to your receiver. Suppose if we are talking about one signal C which is diffracted by a big building edge and reaches to your receiver, and suppose by any small obstacle your signal is being scattered and some amount of signal is being reaches to your receiver. Okay, so at the time of receiving we can have multiple receiving signal at a single time, and this phenomena we can call it as inter-symbol interference. Multipath propagation. Okay, the definition: inter-symbol interference, the energy intended for one symbol spills over the adjacent symbol and it is known as inter-symbol interference. Likewise, in our example, suppose the signal should be in the order of A, B, C, D, but we are receiving our signal A, B and C or B and D at the same time and then after C or D signal. Okay, so whatever we wanted that our signal should be reached to us in a ABCD form, but it is receiving two signals are being received at a one time. So none of your signal is being important because it will create noise, and that kind of fundamental is known as inter-symbol interference. Now next impairment is noise. Noise is anything unwanted signal. It can be divided into four types. The first type is thermal noise. Now this thermal noise is being created by the thermal or agitation process of electrons of your transmitter and receiving device. As we have learned earlier that antenna must be fed, and we are feeding the antenna by higher frequency, higher electromagnetic current, right? So this particular antenna is having the high frequency current and it is converting that current into a electromagnetic waves. So ultimately this process is producing some amount of heat, and that heat is creating the agitation process of electron, and that will produce the thermal noise. And the next type of noise is intermodulation noise. This kind of noise is introduced when you are having the inlinearity between your transmitter and receiver. Your transmitter and receiver are in not proper sequence. They are not following the flow control mechanism. At that time, you can have the intermodulation noise. Third type of noise is crosstalk. Sometime you must hear while on a call, you hear some other person's talk on your line, and that particular noise is known as crosstalk. Fourth kind of noise is impulse noise. This kind of noise is very high frequency amplitude noise for a very short amount of period. Maybe you have heard this kind of noise when there is no proper signal at your TV. Okay, this kind of noise is what? A short period of noise with the very much of higher frequency amplitude value. So this was all about the impairments of your signal, line of sight signal attenuation reasons. But this was all about the when obstacle is present, when there is a physical obstacle is present. But now we are talking about when there is no obstacle present and still you are having the attenuation of your signal. And the first topic is attenuation and attenuation distortion. This kind of distortion or attenuation of your signal is being because of the distance between your transmitter and receiver is very long and you are having no repeater in between them. Okay, so this kind of reduction of your signal is due to the distance, a large amount of distance between the transmitter and receiver. Second type of noise is atmospheric attenuation. This kind of attenuation is due to the atmospheric effect. Likewise, rain could be there, fog could be there. Okay, this kind must be you have also experienced this. Then whenever the rain is there, the network is being reduced. The network traffic is being reduced because of the atmospheric effect. Your signal is not being able to properly reaches to you. Okay, so this is also one kind of fundamental which is affecting your signal to reaches to you. Third kind of fundamental is free space loss. Free space loss means you are having no physical obstacle over here, even though you are having some amount of attenuation. And in this particular attenuation, you are considering that antenna and receiver and transmitter distance is there, atmospheric distance is there, and even also your antenna gain at transmitter side and your antenna gate at receiver side both are taking part in it. If you're not sending your signal with efficient amount of strength to be reaches to your destination or your receiver, then also your signal cannot reaches to your receiver. So the antenna gain is also having some more important on your signal strength or attenuation. Okay, so this was all about when obstacle is not there. Now, due to this particular effect we are having, due to this attenuation we are having one effect which is known as fading. Fading means reduction of signal strength of your signal in the form of amplitude, in the form of frequency or in the form of phase. Any reduction or quick changes in your signal, in your sending signal and receiving signal is known as fading. You can see there is the blue diagram with the distance noise, distance loss. Okay, the particularly pink diagram is for shadowing and this is the multipath fading. Okay, ultimately what we are having the reduction in amplitude, we are having the changes in your frequency and phase value. Okay, so this is what fading. This fading can due to any of the previous effect. It can be due to the multipath fading, it can be multipath propagation, it can be due to your noise interference, it can be due to any of the impairment effects. Before learning about the fading, we must need to understand some of the important definitions, which are, first one is coherence bandwidth. The coherence bandwidth is nothing but the bandwidth of your transmission channel. We are telling about the transmission channel and that bandwidth of your transmission channel is known as coherence bandwidth. Delay spread means due to this particular impairments or attenuation, your signal is reaching with some amount of delay and that delay is nothing but the delay spread. Suppose your signal must be reaches must be reached to your receiver in 4 seconds. But rather in 4 seconds, it is reaches to your receiver in 6 seconds or 5 seconds. Okay, so the difference between that is known as the delay spread. Next one is Doppler shift. Doppler shift is nothing but the shift of frequency at receiver side. We are sending our signal with some amount of frequency, but at receiver side we are having some amount of change in your frequency, and that is known as the Doppler shift. Next is RMS delay spread. The RMS delay spread is nothing but the root mean square of your delay spread. There are basically two types of fading. First one is small scale fading, basically dependent on when the transmitter and receiver distance is small. Okay, and second one is large scale fading, in which the transmitter and receiver distance is very large. Now we are not learning about the large scale fading, we will just looking for the small scale fading. Small scale fading is further divided into two types, again according to two different characteristics. First of all, based on the time delay spread, it is being divided into flat fading and frequency selective fading. Flat fading and frequency selective fading, and according to the Doppler shift, it is further divided into fast fading and slow fading. So now we are looking for this four type of fading in detail, which is being asked in your GTU examination multiple times. Okay, now first of all, what is flat fading? Learning about the fundamental of flat fading. In flat fading, your transmission channel, that is coherence channel, your coherence channel bandwidth is very much of large amount than your signal bandwidth. Then at that time, this kind of fading is being occurred. So you can see, suppose this is what my transmission channel bandwidth and this is what my signal bandwidth. As we have learned in your unit 1 definition of bandwidth, I have told you that we will consider the bandwidth fundamental with the example, with the real life example of water pipeline. So we will assume that your transmission channel is nothing but a water pipeline, and the radius of your pipeline will be considered as the bandwidth. Okay, so this much amount of radius will be considered as bandwidth. This fundamental is a kind of not real kind of fundamental, because I have earlier told you that we cannot represent bandwidth on a paper, we cannot represent spectrum on a paper, right? But we are just looking for the concept of your particular topic, so that for that particular concept we need to just consider that your bandwidth is a radius of your cylindrical water pipeline and your signal is water. Okay, so basic example, if we think about, this is the small pipeline and this is the large pipeline. When I am transmitting the water from small pipeline to large pipeline, the water will occupy whole the available space. It is not like that previously it was having this much of place, so it will continue with that particular place only. Okay, water will occupy whole the available radius, whole available bandwidth. So ultimately, whatsoever your signal is, it will occupy whole bandwidth of your available channel. So this is true for different kind of different frequency dependent signal also. This is true for different frequency dependent signal also. So look over here, this frequency was suppose large and this frequency was small, but still at the time of transmission channel, both the frequencies being altered or faded. Both the frequencies being altered or faded. That's why it is known as flat fading. Okay, all the frequency component, regardless it is having already higher frequency or lower frequency, all the frequency component will have the effect of fading at the transmission channel. So it is known as flat fading. Basically, we have learned that this is your signal bandwidth and this is your coherence channel bandwidth. The signal bandwidth is very much of small amount than your coherence bandwidth. So what will be the outcome of it? Your signal channel time will be higher than your transmission channel time. Transmission channel time is being calculated as per the root mean square of delay spread, and the original signal time is being calculated as the symbol time. This is what your symbol time will be greater than your RMS delay spread. Okay, so this is the about flat fading. Same as we are having the frequency selective fading. The frequency selective fading is having totally inverted fundamental. Likewise, your transmission coherence bandwidth is lesser than your signal bandwidth. Okay, suppose this is what your water or your signal. Okay, I am having available pipeline in my signal in very large amount of, but in transmission channel it is short. So I need to reduce the frequency for the transmission purpose. Okay, but what about the another kind of signal which is having already lesser frequency than your signal? So it will propagate as it is. It will not have any effect of your fading fundamental. So that's why it is known as frequency selective fading. The fading effect will be occurred on some selective frequency only. Okay, fading effect will be occurred on some selective frequency only. So here it is your fundamental. Your signal bandwidth is very much of greater than your coherence bandwidth. So your time spread, symbol time of your signal will be lesser than RMS delay spread. Okay, this both are vice versa. Next one is fast fading. Suppose we are considering that here the bandwidth, coherence bandwidth and signal bandwidth both are same. Okay, but this signal is slower than your transmission channel. The signal is slower than your transmission channel. Likewise, symbol time period is higher than your coherence time period. Okay, symbol time period is higher than coherence time period. So at that time, suppose this is what my signal. Okay, but at the time of transmission it is going in very fast, and again it will be as same in your transmission side. So ultimately it is also having effect that bandwidth of your signal will be greater than Doppler bandwidth of your coherence channel. Okay, we have just assumed previously that both the bandwidth is same, but ultimately the effective bandwidth will be changed. Okay, according to the symbol time period, because both are vice versa. Same in slow fading. Slow fading is having the same fundamental. In your transmission channel bandwidth is very high, but at your transmission channel bandwidth is very low, but your signal bandwidth is very high. Okay, same fundamental. Your signal time is very fast, but your transmission time is very slow. At that time, what fading is being occurred is known as the slow fading. Same, your signal time is very slow, but coherence time is very high. So that means this channel is slow. So vice versa, your bandwidth of signal will be higher than your Doppler bandwidth. So the summary, we have learned about all the impairments of line of sight propagation. Then after, we have learned about the fading, okay, in which in detail flat fading, frequency selective fading, fast fading and slow fading. Thank you. We will meet in our next lecture.